Okay, let's start with this lecture and one announcement that in the next lab section, uh, we will do the lab, but we will do something that I will assign to you. I will maybe share a document on the blackboard, which will have the lab activities that you have to perform. And then after performing those activities, you have to upload your final answer on the blackboard. Okay. So you have to bring your laptops with you. Okay. So from here, so the old lectures uh, from this topic, the old lecture are also the links for those lectures are also given, but I will update these links because these are old ones. Some topic it can happen that some topics would not be the part of the slides, huh? So I am recording and then I will update these links. So now we are here at CO3 and uh, I'm sure that we have already seen the greedy batch first search and the A star algorithm, huh? Okay. So that's why now CO3 or CLO3, the statement of the CLO3 is illustrate the performance of local, global, and optimal search strategies. So now in this CO, we will see these different strategies of search and we will see some algorithms related to it. So what is optimal search, what is global search, and what is local search? First, we are going to see the definitions for them. Optimal, the word optimal you already know, and for example, in previous CEO, and when we were saying that this algorithm is optimal, it means that algorithm can give us the best possible solution. So optimal search is again the same definition. So we have to, so in optimal searches, we will have such kind of algorithms in which we have to find the best possible solution in any given state space. State space meaning problem. Problem has its area of expansion, you can say. So optimal search will always give us the best possible solution. And then the global search. So for each problem, we will have a state space. We already know what is the definition of state space, huh? The set of actions and the set of states. So anyhow, so for any problem, some state space, we will have a state space. And then if we are going to explore the entire solution space or the state space for finding the solution, huh? If we are going to explore the whole state space for finding the solution, then this type of category would be called global search. And here in this global search, we will search for global maximum. And we will see what is the definition of global maximum, okay? That is like a maximum number in an array, okay? If I say minimum number in an array, that is a kind of local, huh? Local minimum. But if I say maximum number of an array, then it would be like, this is not an exact example, but I'm just giving you a hint to start with. So if you are going to explore the whole state space for finding the global maximum, or you can also call it optimal solution, huh? Or global optimum. There are different words. Huh? If I say global optimum and if I say global maximum, Both are same. Okay. Both are same. So if we are going to explore the entire or the whole state space for finding the solution, and that solution would be optimal, then this kind of search is called global search. Similarly, for local search, we will have a state space. For the local search, we will have a state space. We will start with some random initial state, you can say, or initial state. We will start with an initial state. It can be random, sometimes it cannot. And then we will have a step like increment, or you can say incremental step. Then we will have next step. And in the next step, we will see that in the next step, we have improvement from our previous state. If improvement, we will adopt this improvement. And we will have then next step, you can call it increment. And then you will see, okay, step two has improvement with respect to step one, then you will adopt the improvement. And then you will see step three, which is the next increment. And then you will see, do we have an improvement on step three as compared to previous step two? If you have an improvement, you will adopt. If not, you will not. And you will go like this. And you will go like this. So we will start with what? A random solution or initial state. So you are giving some state into the initial state. You are calling it that it is our solution. And within with next increments on each increment, you will have improvement in solution. You will take it. Otherwise, you will not. So you are going to start with the random state or random solution. And then by making small increments or small incremental changes, you are going to find optimal solution, best possible solution. When you will have the improvement, you are going towards the optimal solution. Huh? So this is called local search. And we are going to start with local searches. Okay. We are going to start with this local search. Then we will have the global search. And the optimal search we already know from that previous CL. So basically, this chapter is about local and global searches. So, yeah, you can say. But sometimes there are some deficiencies in local search, and there are some deficiencies in global search. You will see these differences. There are some algorithms in local category. This one, first one, which we are going to see, and this is sometime it will try to give us the optimal solution, but most of the time not. You will see the differences. So now we are going to see the local search. And there is a property of the local search. What is that? That in local search, if we are going to start from the initial state and we are going to reach at the solution, then from the initial state up to the solution, we will have some kind of a path. But in local searches, we are not going to store the complete path from initial state to the solution state. We are not going to store it. We will not going to consider it. What we will consider only the current state. Whatever the steps is, we will only have the current state. Okay. We will not take care of any previous states. We will only have to consider the current state and what are the neighbors of it, the next neighbors, not next to next, huh? Only the immediate next neighbors. So we have to take care of current state and the next neighboring states in this local search. So now we are going to see the first algorithm, which is hill climbing algorithm of this local search category. The name is hill climbing. So first, when we will go into it, we will see some things related to hills. Huh? But later on, you can apply this algorithm where it fits. Okay. So you can apply this algorithm in any domain. It is not something you have to apply this algorithm due to its name only on hills. Huh? Anyhow, so what this algorithm do, it will start. It will start with some random initial state because this is the property of the local search. And then it will go in the direction of increasing value, which means improvement. Huh? In all steps, it will try to have improvements. This is the definition that you have seen here. Huh? So it will start with some random initial state, and then it will move on to the next steps in the direction of increasing value. You can call it like it is a uphill direction. Huh? Like if you are moving on a, if you are, for example, if this is a hill, so you start with this and then you are going like that. Huh? So you can say it is like an uphill, but take it as conceptually only. And then you will terminate the algorithm when you will reach here at the peak of this hill. Okay. When you will have the, which means when you will have the maximum improvement, and that maximum improvement is possible according to this diagram only at the peak. Huh? And after that, you will have the lesser values. After that, you will have the lesser values. So this algorithm will start with a random initial state, and then it will go into the direction of increasing value. And this algorithm will terminate at the peak where you will have the maximum value, or you can say where you will have the optimal solution, where you will have the optimal solution. And there is no any further neighbors. You will have the neighbors here. Huh? You will have the neighbors here, like points here. Huh? And there is no further after this peak there is no further neighbor with higher value. Okay, all the neighbors will have the lesser values, low values than this. Anyhow, and we know that according to this local algorithm, we will only store the current state and its neighboring state, immediate neighbor state of the current state. We will store only this one. Okay, what are the issues? What are the issues with this hill climbing? This is a local search algorithm. So this hill climbing is good for finding local maximum, but not global maximum. What it means? Uh, Here you have something, some diagram. So then this is the highest peak. This is one peak, this is another one, and this is another one. Huh? But this is what? This is the highest peak. Or you can say these are the highest values if the algorithm is going on in execution. We call it global maximum or global optimum. Hmm? And then what is this then? If this is the highest peak, this is called global maximum. What are these other peaks? This one and that one. So then other peaks would be, you will call it local maximum. Okay. You will call it local maximum or local optimum. This is also a local maximum. This is also a local maximum. But its different is its shape is flat. So we are calling it flat then. So its shape is different from these. Okay, no issue. But again, it is a local maximum. It is a local maximum. But this is what? This is the highest. So we will call it global maximum and all others. So there would be one champion, huh? And then others would be the normal local players, huh? Anyhow, so this is global maximum. You have to memorize these terms. Global maximum, global optimum, same thing. Local maximum, local optimum, same thing. But local optimum can be, yeah, it can be more than one. Even global maximum can be more than one, okay? If they are equal, huh? If they are same. Anyhow, if you have, I will come back to here, but anyhow, let's see. So if this is the highest peak, and if you have something like that, for example, this is the head of mine, and then I have something like that, huh? So that is like a shoulder, huh? This would be called what? Shoulder. Because here you can have points here, okay? You can have states here, which will go like that. Some point here, some point here, some point here, and similarly you will have points. You will have points here. Like here, this circle is a point, huh? So you can imagine you will have the states here, and then you have to go through those states. This is a two-dimensional, so that's why I am drawing only two-dimensional. If it would be three, then I will draw some points here, huh? Or n-dimensional, you can say. Then I will draw some points here. Anyhow, so this is called the shoulder. This is global maximum, local maximum. And if the peak is flat, you can call it flat or local maximum. It is local maximum, but surface wise, it is flat. And the points can exist over it like here. More than even 1 points or only 1 point on the surface. Okay, here, for example, here in this diagram, we have a circle here. So we are calling it that this is the current state. This is the current state. And this is the objective function. Objective function can be anything, which means finding the highest point. So then this would be the height, huh? The y-axis would be height if we have to find the highest point. And it can be maximum number in an array. Then you will have the numbers here, huh? Or anyhow, so let's now another point. Another point. What is the deepest point here? I can see from this diagram that this is the deepest point, huh? Deepest, lower, deepest point. So this is the deepest point. If this is the deepest point, then what you can call it? Global minimum. Okay. So that is maximum, and then this is the deepest. So then this is called global minimum. It is not written here, but two possibilities always are. So maximum, minimum. And then what is this then? This point, local minimum. Okay. Local minimum. Now come back here. So now you will understand this point, what it is saying. So what are the problems with this hill climbing? Even we don't know what is this hill climbing, but what are the problems? This algorithm is good for finding local maximum. Then you can understand that it is good for finding this one or this one, huh? But it is not, it is not guaranteed a global maximum, because there are some issues in the approach, in the strategy of this algorithm, that it will not reach at the global maximum. So that's why it is written here that it does not guarantee the global maximum. So here, this global maximum, if you want to find through this algorithm, then it is not a guarantee. Okay. But you can reach. But you can reach. How you can reach? When we will execute this algorithm, then you will see. And there are other issues in that this algorithm can lost or can stuck, or can lost, or it can terminate on a plateau. Plateau mean flat surface. It can be flat surface or shoulders. So if you have something like that, flat surface here or here, which is shoulder, then this algorithm can terminate. The word there is lost, okay, but it can terminate. It will stop here and it will give you whatever it has as a solution. So let's see this algorithm. This is a small algorithm like a finding a maximum number in an array, nothing else, okay? But this is the basic version. This is the basic version. Then people have done some new things in it, and then those things will have the new names, the same name, but they are the variants of this algorithm with the new names. So for example, here, this is the hill climbing. We are passing any problem into it, and it will return what? It will return a state that would be what? Local maximum. Local maximum is guaranteed. Okay, local maximum is guaranteed, but global maximum not. So that's why here we are only writing local maximum. And if you will execute this algorithm in reverse direction, it will give you local minimum. Okay. So anyhow, so first we are putting the initial state of the problem into this current variable. For example, if I have the points here, I'm not drawing complicated things. I'm just drawing simple things, okay? Because here we want to understand. Otherwise, we can put some complicated things here. These are my points, you can say. Okay. So, for example, this is now my current state, which is drawn here. Huh? So this initial state is now in the current variable. Done. While true, so this loop is true forever. And then do take the highest value successor. Successor mean neighbor coming next. Huh? Take the highest value successor state of the current. So the next state of this current state is this one. Huh? This one. So I'm changing the color now. So the next state is the next higher value is this point. So it will take that and it will store in the neighbor. And then we are checking that the value of the neighbor is less than the value of the current. This, if you have the value, if you know that if you have value 0, 1, 2, 3, 4, 5, 6, something written here, and if you have 0, 1, 2, 3, 4, 5, 6 written here, huh? Or only this. So then you are checking that the value of the neighbor is less than or equal to the value of the current. This is the current which is lower and this is higher. So value of the neighbor is not less or not equal. Huh? So then what? The value of the neighbor is higher. So this condition is what? False. This value of the neighbor is false. This condition on this status, this condition is false. So then this will not happen and we will come here. We are updating the value of the neighbor in the current because we have an improvement. Huh? So it will take the improvement, and if you will not have the improvement, it will discard. So it will take the improvement and then it will go to that while loop. It is true, and then you are coming again. Take the highest value successor state again. Now in the next point, you will take this value which is at the peak, put it in the neighbor, and then you are comparing these values. Value of the neighbor less than or equal to value of the current. Now this previous point is current, and this is the neighbor, and the value of the neighbor is higher. So again, this condition is false, and then we will come here and we will put the value of the neighbor into this current, and we will move on here. And then take the highest value successor. We don't have that higher value successor, huh? Because here it is lesser. We already considered it is also lesser. We don't have any value. So then what? Here you will not have any value. Here you will not have any neighbor. Here you will not have any neighbor. And then here, if this condition will check, you will have the previous value of the neighbor and the previous value of, so this is the updated value of current, but you have the previous value of the neighbor, huh? So basically you have this value here. Now in your current and neighbor, you will have this value which is at the peak. And then here you are checking value of the neighbor less than equal to value of the current. The values are equal, huh? Condition is the values are equal. And if the values are equal, you are returning the current variable. You are returning the current variable. And that would be what? That would be local maximum from this algorithm. Only the terms are difficult. Otherwise, it is what? Finding a maximum number in an array. It is what? Finding a maximum number in an array, nothing else. Moreover, now take another situation. If you have, for example, those points can be here. For example, here I will start from here, then I will go there, and here you will have 2 points or 3 points with equal value. Okay, when you have points on the flat area, they have the same value, huh? Because it is flat. Anyhow, now, so we are putting the initial state again into this current. So now this is our initial state, putting it here, while true, and here take the highest value. Okay, I will take this value and put it in the neighbor. Here I am checking neighbor less than current, no, condition false, and then I am updating. So now I am here. And then after that, I am going to this loop. While true, take the highest neighbor. So now I am taking this number, which is here on the peak, the first one. So now it is becoming neighbor, and then I'm checking neighbor is less than equal to current. No, neighbor is higher. So then what? I am putting this value here in the current. And now this is my position, huh? And then I am going again to this while loop. And then take the next neighbor. And then here I am taking this value. I am taking this value. Previously, this value is in the current. But now I am taking this value which is on the flat area. So I am taking this value, putting in the neighbor, and then I am checking neighbor less than equal to value. No, it is equal because on the these 2 points on the flat area and have the same value. Huh? So then what? It is equal. It is basically equal. If equal, then return the current. Whatever it is current is the previous value. So then it will return through this algorithm. So that solution would be local maximum. And similarly, if you will have the points here if you have only one point and then point here, if you will execute this algorithm on these points, it will give you finally this point. It will give us finally this point. So it is a possibility that through this hill climbing, you can get the global maximum. But then our starting point should be on this mountain, not here. Huh? This is the thing. Our starting random initial point should be on this mountain. And we don't have multiple values here on the shoulder. If we will not have multiple values here, then surely we will reach here. I tried to present you all the possibilities. Maybe some options left, then we will cover those things in the next upcoming slides. Now, another example of this algorithm. Another example. So now the same algorithm here is written theoretically here. Theoretically means in sentences. Here, define the current state at the initial. This is the same. Whatever the initial, define this. Loop until the goal state is achieved, or no more operators can be applied. Okay, that is that loop, same loop, the same loop. So this is the initial, this is the loop. And then These steps are under this loop. Apply an operation to the current state and get a new state. So get a new state, which is like get a higher successor. Huh? Compare the new state with the goal. So you are with the goal. This is a new statement. Huh? Here we are not comparing it with the goal. Huh? We are just returning. So okay. So now this is a new statement. This is extra statement here. Okay, no issue. So whatever the state we are getting here, we are comparing it with the goal. That if it is a goal, then we will go out of this algorithm. Okay, quit if the goal is achieved. So now here, if you achieved the goal, then quit. That is the simple state. And then okay, so you can merge these two values into one statement. And then we have this. If it is not goal, then evaluate the new state with heuristic function. Here in this algorithm, now we will consider some heuristic function, okay? We will evaluate the state with the heuristic function, compare it with the current state. So here, what we are comparing, less than or equal to. So here in this algorithm, this is the heuristic function. Huh? This heuristic function can be different in different algorithms, okay? It is according to your, if you have something, if you want to do something different, but actually you are applying hill climbing, but you are checking maybe that in the sentence you have some string in it or not, huh? So you can have a different mechanism. So this condition can be different. This condition, which I am calling it heuristic function, this can be different. But actually it is a, so here you are comparing. So this statement is similar to this one. And then you are checking if the newer state, if the new state, if the neighbor is close to the goal, is closer to the goal compared to the current state. So what it means that the new state or the neighbor state has given you improvement. If you have that improvement, update the current state. Huh? If you have, it is like that. You are updating the neighbor into current. So this is the same thing written here. But here we have not mentioned less than equal to. We are saying heuristic function. We are saying heuristic function, and it can be different. And here we have a different problem. In this example, we focused on the execution of the example, not on the algorithm. Our focus is not on the algorithm. Our focus is not literally statement by statement on each statement. So here, this is our initial state of the problem. And we want to reach here. This is the goal state. If you will see here, A, D, C, B. So this is something random, no any order. And in this goal state, A, B, C, D. So A is at the bottom, then B, C, and then D. So they are properly aligned. They are in ascending order and stacked on each other on this goal state. So we have to reach here by applying this hill climbing algorithm over this example. Okay, over this example. And hill climbing is what? The category of local searches. The category of local searches. So you can apply the category of local, whatever you have studied in the local search, you can apply that concept over it, or you can also apply some global strategy here. We will see. Here, first we are going to apply the local heuristic function. If our heuristic function, I said heuristic function can be different, huh? So if our heuristic function is something like that, what is this? Awarding each block. So this is called block. Awarding each block in a new state. So we will start with this initial state. If I will do, maybe if I will move this A down, so this is, I have applied one operation, huh? And then I got a new state. Then I got a new state. So then what? Now you will understand, awarding each block in a new state. So whatever the new state you will have, you have to award each block with +1. If the condition is if stacked on a right block. If stacked on a right block or place. So after performing one operation, if each block is on a proper position or placed on a right block or stacked on a right block, then you will award +1. And if it is something wrong with it, then you will award -1. You will understand through this example. Here, this initial state, ADCB. So we have ADCB here. So now this B. So you have to check this B is on a right place according to this goal state, huh? So this B is not on a right place. B should be after A, you can say, huh? So this is not the right position for the B. And if it is not the right position, if it is not stacked on a right place or block, then what? Award penalty. So that's why it is -1. And then this C is stacked on a right place. C is tagged on B. So C is tagged on B. So that is its right place. Huh? We are not considering A yet. We are not going for too far. Huh? We are just checking the neighbors, huh? Immediate neighbors. We are not going too far that A. We are not considering A. Leave it. Don't go too far. Huh? Just check the immediate neighbor. So this B should be on A, but A is not here. So that's why this is not the right place. So we are awarding it -1. And then this C should be on B according to this label. B should be, this C should be on B, stacked on B, which we have here. C is tagged on B. So that is okay. So that's why this is the right place. We are awarding +1. And then now this is our heuristic function. Our heuristic function is different. It is not less than or equal. Heuristic function is different. Heuristic function is different. We have the same algorithm and we are solving a different problem here, which can be a puzzle. Huh? So now D is on a right place. D is tagged on C. According to this global, D is tagged on C. So that is the right place for the D. So then we are awarding +1 according to this local heuristic function. And then A is tagged on D. Is it the right place? No. A here, huh? And after D, we don't have anything. So then we are awarding -1. Then we are awarding -1. And if you will sum them up, you will have what? The answer 0. After D, you will have what? So we have A, then what? We are not talking about cycle here, okay? Don't go in that direction, okay? Don't go too much deep. Huh? We are not considering graphs here. It is simply blocks. Huh? So if you will sum up these L values, you will have the 0. So now the heuristic cost of this state, this is a state, huh? Of this state is 0. I can call it that the heuristic cost of this state is 0. Now, algorithm will, so now this is our, you can say this is our current state, initial state, huh? Which was Now algorithm will do what? It will get a new state. It will get new state by applying what? By applying some operation over it. Okay. Then what operation I will apply? I will move this top block down. And here in the next state, the top block is down here now. I draw these pictures specially for you, okay? I spent maybe anyhow, so that it will be easy for you. So, okay, I moved in the, so now this is a new state. In this new state, according to the algorithm, in this new state, A is now down. I moved it down, huh? This is my operation. And then you have to check that this new state is equal to goal, compare it with the goal. If goal, quit. No, it is not a goal. So we are not quitting, huh? And then what? Evaluate. So now this is the new state. Evaluate it with the heuristic function. Okay, now I will calculate their values, huh? So B is on the right place? No, it is still -1. C is on the right place? Yes, it is still -1, the previous value. D is at a proper place? Yes. So it is still +1 according to this previous values. And this, what about this A? A is on the right place according to the goal state? Yes. Now it is on the earth, you can say, on the ground, huh? So it is at the proper place. So that's why we are assigning positive +1, huh? We are rewarding. We are not giving it penalty. So, and if you will calculate plus 3 minus 1, you will have the final heuristic cost for this state is what? The heuristic cost for this state is what? 2. You are getting the heuristic cost of this state is what? 2. And now you will compare this heuristic cost with the previous one. 2 is improvement or not as compared to previous one? Improvements, yes. It is what? It is improvement. And then you will keep this. Your hill. So you will compare it with the current state. If the new state is closer to the goal or gives you improvement in easy words, huh? Then update the current state. So now we have updated from this state to this state. And I am removing this whole drawing again. So now I updated, the algorithm moved from this state to this state. Now this is the current state, huh? Now again, but it is still not a goal. Then algorithm will do what? It will move to it will get a new state. How we can get? By applying an operation. What is the operation? Movement, huh? So then I will move this D down in the next step. B is not a place, the previous value. C is also the previous value. You don't have to think too much, huh? Take those previous value. And now here A is proper place. Yes. The previous values. Now what about D? D is on a proper place. D should be stacked on C according to the goal. So this is not a proper place. So then I will award what? -1. And if you will add again, then you will have what? 0. Heuristic cost for this state is 0. Heuristic cost for this state is 0. So now you are getting new state, you are comparing with the goal. No, comparing. So this is the new state and this is the previous is the current. So this is new and the previous is current. You are comparing with the previous. You are not getting any improvement, huh? And when you are not getting any improvement, if newer state, then what? This will not execute. And you will go again to this loop. Loop until the goal state is achieved or no more operators can be applied on the current state. So on this operation, okay, I can apply a new operation, but according to the hill climbing, according to this algorithm, when the new state is less than or equal to current, yes, it is less actually. The new state has here Here the zero is less than this current. This is current and this is new, huh? So when the new state has less than the current, return current. So then according to this hill climbing, it will return this state and it will go out of the algorithm. According to the simple hill climbing that you have seen here on this previous. It because you don't have the improvement according to that previous state, huh? Even you are going down. So this is one possibility. So you can, okay, if this is one, so you can move the D down or you can move the D here, okay? This is another possibility. You can move the D on A block. Okay. So that's why we are considering that state here, nothing else, okay? Nothing else. Otherwise, our algorithm is stopped here. It is giving us this state. And if you moved your D on A, then this would be the situation. We are checking that maybe the heuristic cost would be different. So BC is same, okay, the same with the same value. A has a proper position plus value. D is on A. D is on A is not a right position for the D. So that's why we are assigning it -1 after calculating this positive, negative. So again, it has the heuristic cost 0. So with both of these possibilities, so because according to this algorithm, if no operators can be applied, if no operators, so if operation is possible, then apply that. So that's why we are applying this operation, huh? And if you apply all the operations, all the states that you are getting now, this one or this one, so sorry for that. So these new states are not giving us any improvement according to that previous, which is I'm calling according to this algorithm, I'm calling it current state. So these states are the new states, and this is what the current state, and this is what the new state. And I'm comparing new is not giving us an improvement with respect to current. When this condition will hold, you will have to go out of your algorithm according to this hill climbing. You can also compare with this one. No improvement. Okay, go out of this algorithm. So this is the execution according to local heuristic function. Now, global heuristic function. Now we are changing our heuristic function, huh? The problem is same. And the global heuristic function is award each block in a new state with +1. Whatever the new state will come, then you will have to award each block the values. And what is that value? With +1 if placed correctly. If placed correctly, otherwise -1. Otherwise -1. This is different from that. Previously, you were considering only one neighbor. You were not thinking deeply. Here you have to think a little bit deep. Here you have to think. Here in the beginning, so this initial state ADCB, ADCB, so that is the same initial state. And here the B, which is on the ground. So is it placed correctly? The element which would be on the ground, okay, that is exceptional here now in this heuristic function. In this heuristic function, the block which is on the ground level, you can say, which is on the ground level, that is now an exceptional case. You have to give, you cannot decide because it is not on a block, okay? It is not on a block, so you cannot decide that either -1 or +1 or whatever. So then what? Here you will have to give the value 0, okay? Maybe I have to write this here within this global heuristic function, huh? Maybe I have to mention it. But now keep it in your mind that the block that would be on the ground, the value for that is 0, okay? That is like a neutral, huh? You cannot say that it is placed because there is no any block under it, so that's why you cannot say any answer according to this heuristic. I'm not saying with my own, okay, according to this heuristic. So now this B is on a ground, so that's why we cannot say it is properly placed, because actually according to this goal it should be on A, but A is not, that situation is not here. So then what? We are giving 0. So we are remaining neutral and we are giving 0 here. Now for the C is on a proper place, C on B, okay. C is on a proper place. Yes, C is on a proper place, but there is a difference. So if C is on a proper, is stacked on B, but B, for example, here I am checking that C should be on the third level, and here C is on the second level, huh? So according to the goal, C should be, if these are the two blocks under it, and here we have only one, so then 2 minus 1 you can say. So then 1, so this one thing is clear, that here the position of C is not properly placed according to the goal state, because C is what? At number 3, at height number 3, huh? And here C is at height number 2. So but you have to find the difference. So here it is 2 blocks and here it is only 1 block. So the difference is almost 1, huh? And it is also not properly placed. So now that is what I was saying, that you have to think deeply, huh? So then, so as it is not, the position of C is not proper, so that's why we are going to give penalty, okay, not reward, okay? But how much penalty? So here, so C is only 1 block, is placed with a difference of 1 block. Can I say C is wrongly placed with a difference of 1 block? So I am writing that -1 here. Clear? Now think for the D. So D has the position at 4th height, or you can say at height number 4, which has 3 blocks under it. But here D has 2 blocks under it. So this is the 4th position, and here 2 blocks. So and here the D is at number 3. And what is the difference then? What is the difference of 2? So here you can see D, here D is at here, and here D is here. So C and B, and if we will have the A, then C and B, you have to move it a little, 2 steps above. So the difference from the goal of this D is then what? -2, because you have to move. For example, again, if I will put A here, huh? Then you will move this B here, and then you will move this C here, and then this would be the point of D, huh? So you have a difference, what? You have a difference of 2, that is written here. And now for the A. So here A should be at the bottom, huh? But here A is there. So then what? A is here. So if if you have to move these 3 blocks ahead, and then you have to move it down. So the difference is -3, 3 positions. So again, if I will repeat it with other words, B is properly aligned, I cannot move it further down, so that's why you can say it is 0. Huh? C is properly aligned according to this goal. I I have to put A here, and then I have to move this B here, and then C. So that is the difference is only what? 1. Hmm? I have to move B 1 point above, and then C, then it would be okay. Huh? Now I am saying something according to this movement. Now the D has the proper position. No, I have to move this C up. I have to move this B up, and then I have to place A here. And how many movements? So this movement 2, which is written here. Now these other words will give you understanding maybe easily. Yeah. Now A is properly placed. No, I have to move this D up. I have to move this C up. I have to move this D up, and then A. Huh? So I have to do 3 movements, which is mentioned here. So this movement means it is wrongly placed. So then you have to give minus penalty values, huh? -3. Sum them up, and you will have the cost, heuristic cost for this global heuristic. Why global? Because we are searching all the possible option, huh? We are not focusing only the next neighbors, huh? We are considering, exploring all the, what is the global search? Exploring an entire solution space, huh? So we are basically, if we are going to make this hill climbing a global search, then this is the heuristic function. This is also another thing, huh? But according to the algorithm, this hill climbing lies in the category of local searches. Anyhow, so here the heuristic cost for this initial state is -6. Now the algorithm is still same. So now I will do the movement. I will move this A down here, and I will keep those previous values. So 0, -1, -2 as it is. But what is the value for this? A is now on ground. Is it properly placed? A is, yes, it is properly placed. Huh? I should have to, this is -3. I have to think it, huh? Just a minute. Okay, so now we have finalized that this is also the part of heuristic function, that whenever the block is on the ground, then it has the value 0. So even we can say that A is at a proper position according to that previous concept. We can award +1 here. This was little confusion which was appearing into our minds. But our heuristic function is that whatever we will get, this is also the part of heuristic function. I will rephrase these sentences so that it would be more clear. So whatever the blocks would be on the ground, the value for that would be 0. So that is the reason that now A is here and it is on the ground. If I can say it is on a proper position, yes, it is. But is, and then you can say it is on the ground. So that's why we are saying giving it the value 0. Okay. So now this has the heuristic cost -3. And now this is the new state, comparing it with the previous. Is this state giving us improvement? Yes. So then we will consider this state as current. Huh? And then our algorithm will find a new state. In the new state, we are doing what? We are moving this D further down. Huh? And here. So this is our new state now. This is our new state. So this has the values according to those previous values, 0, -1. Okay. This is on the ground, value 0. This is on the ground, value 0. What is the total cost then? -1. -1. So now this new state as compared to previous current state giving us improvement? Yes, in the values, it is giving us improvement. So then what? Now this state is the current state, and now the algorithm will find a new state, and this is the new state. And in the new state, we will move this C further down, like here. And everything is now on the ground. And if you will assign them the values, the heuristic cost, final heuristic cost for this state would be 0. And this new state is giving us improvement with respect to this previous current state. Yes, it is -1, it is 0. So then what? We are considering this new as a current, huh? We are updating the state. So still continuing here on the next slide. So here, this is our current state now, which has the heuristic cost 0 from the previous slide. Now this is the current cost. Algorithm will find now the new. So everything is now here. Now what algorithm will do? It will go towards the goal state. Huh? So now here we will put, or we will stack, or we will place this B on A, huh? In the next step. And now this is the new state. We are putting or placing B on top of A. And then, okay, A is on the ground. We are now calculating the values. A is on the ground, value is 0. And now the B is properly placed according to goal. According to goal, yes, it is properly. And if it is properly placed, assign the value +1. So it has the +1 there. How many blocks are placed properly? So this is the proper position for B, and also the block, this A block is also properly placed. No difference. So we are also counting this one, okay? So that's why we are saying 1. And now we are, so this is, if you will calculate the heuristic cost, this one is better than this one. So then what? You are considering this current, and the algorithm will find the new state. In the new state, you will move this C to B here, like that. And here the value for the A, due to the grounded block, you can say it is 0. B has the value 1 previously. C is on a proper position. Yes, C is on a proper position on top of 2 blocks. Okay. So that's what it is, a proper position. Award each block in a new state with +1. So you can say this is the proper position, and then we are assigning values to it according to that previous. You don't have to do any movement. It is properly positioned. If you have to do movement, you have to do the movement with these blocks, huh? If you have to, we will take that movement concept, okay? If you have to do the movement, we have to do something with this, but those are properly aligned. So that's why we are giving this value 2 to it. This is not +1, okay? So because you are thinking not only the next neighbor, you are thinking collectively for all the blocks. Now if you will calculate, if you will sum up these values, so then the heuristic cost is 3. And if you will compare it with the previous one, you have the improvement. So okay, then this is the current, and you have the new state now. In the new state, you will move this D on the top, like here. And then here, up to this, the previous values, then there's D. This D is proper place. Yes, with respect to these 3, it is properly. If it is not, then you have to do something with that. But these 3 are properly aligned. So write the value of this 3 here. And then summing them up, you will have the cost 6. Compare it with the previous. You got the improvement, yes. And then we are calling it current. And according to this goal, you will also match with the goal. When it is matching with the goal, you will quit from this algorithm. Huh? You will quit from this algorithm. Understood? So maybe this statement is, I should have to revise, okay? I should have to revise. I will write with respect to these movements, huh? And then it would be okay. It would be easy in understanding, okay? Otherwise, it is mixing with that previous local heuristic function. Huh? Okay. Now, I said to you that the hill climbing algorithm, this is the simple one. This is the simple one, okay? Like a finding a maximum number. What is that? Okay. So this algorithm is a very simple algorithm, like finding a maximum number in an array. But people have done modification in this algorithm, and when they did this modification, they came up with the new names for this algorithm. So these new names with the little different ideas for this algorithm hill climbing, the new ideas will came up with the new names. For example, and these new names we are calling them the different versions of the basic algorithm of hill climbing, or you can say the variants of the hill climbing, which means different versions. The first version is called the stochastic hill climbing. Then another version is called steepest ascent hill climbing. Then another version is called random restart or shotgun hill climbing. Same thing, huh? So stochastic hill climbing. So we cannot go into these all variants one by one. Okay, we will consider the different algorithm. But now you have seen the basic and what is stochastic. So it will in this hill climbing here in this basic version you are selecting the next neighbor, immediate neighbor, not from next or next. For example, here if this is the current and then you can have something neighbors here, huh? So then if this is the position, if this is the point, then this is the next highest successor. This point is the next highest neighbor. In the downward direction, this is also a neighbor of this point, but hill climbing does not go into downward direction. It always moves in the upward direction. Now let's see what is the difference between this and that. It will select what? It will select randomly. It will select neighbors randomly and probabilistically. So what it means? It means this. So if this and this is the neighbor of this current point, then stochastic hill climbing do what? It can select the neighbor randomly. So it means that it can select this neighbor which is in the downward direction. It can also select this neighbor which is in the up, which is at a highest point. Huh? Basic hill climbing never select this point which is on the downward direction. It always selects higher. Huh? And if it always selects higher, then that is the reason that hill climbing is stucking at the local maximum, is stopping at the local maximum. And if the basic version of hill climbing, if it will reach on the local maximum, then after that it cannot move further, and the algorithm must have to quit. Huh? But if you have this stochastic hill climbing, then here at this point, this point and that point, these are the neighbors of this point. Stochastic algorithm can select the neighbors randomly with a probability value. Leave that probability. It can select the neighbors randomly. So it means that it can select this one or it can also select this one. So in stochastic hill climbing, there is a possibility that you can move down. Huh? So that is the difference. So it will select the neighbors randomly. I have also written the word probabilistically because you can introduce some probability value for each state, and then you can check that if the probability of that state is greater than 0.5, then you are moving to the next. If it is less, then you are not moving. Huh? You can introduce something like that, but leave it. Even this random selection is giving you the idea that this stochastic hill climbing is different from the basic hill climbing. Huh? Because stochastic hill climbing allows moves in the downward direction, but basic hill climbing does not allow moves in the downward direction. It always go uphill. Now, steepest ascent hill climbing. Steepest ascent hill climbing. So it is again hill climbing, ascent and descent. Descent is moving down, ascent is moving forward or something. Okay. But here ascent doesn't mean that moving forward means always up, huh? Like we were discussing that hill climbing always go in the upward direction. This ascent means always in the forward direction, huh? Steepest. Steepest here means the most possible forward way. What it is now, see what is the difference here. You know what is the basic hill climbing, huh? Now, if this is the current point, if the neighbors of this point is 1 here, okay, and okay, and another point is here. If I will consider 3D, then I am drawing some points here. Another point here, and if another point is here, and if these are the next neighbors, I am drawing the tree so that you will have the idea. So this is the current position, and then you have these points, and this is the local maximum, for example, you want to reach. Huh? And then you have further points here, but it is not the neighbors of this one. Huh? Steepest ascent will do what? It will, here the algorithm is here at this state, and it will see this and all these 4 points it will see, and then it will see what is the point which is more close to the goal, you can say. So like greedy best first search, huh? Like greedy best first search, or another way, from these neighbors it will see that which neighbor is more close to this goal, and which neighbor is more close towards goal, it will select that neighbor. Okay, it will select that neighbor. So it can select this neighbor, this, but it will select this because it is more close towards the goal, because the distance towards the goal is now minimized, you can see. So that is what this steepest ascent hill climbing, no, hill climbing do. So it is a like a mixture of greedy best first search and the hill climbing, huh? So it will evaluate all the neighbors from the current state, and it will move to that neighbor which will give you highest improvement. Okay. which will give you highest improvement towards the goal, you can say. And it will leave all other neighbors and it will select that neighbor which is giving you the highest improvement. So that is the steepest ascent hill climb. Then random restart. Random restart, the other name is shotgun hill climbing. So the hill climbing algorithm can stuck on a local maximum. This is what we know that. So if you are executing this simple hill climbing algorithm over here, I will get this as a solution, and after that I will not get any solution. But if you are finding global maximum by using this algorithm and your current point is here, you will not get this global maximum anymore. Then what is the solution? Some person came up with this idea, then okay, and previously I started from here. Then if I will stuck on this local maximum, I will restart the algorithm again with a random initial state. So then I will restart and the algorithm will select its initial state randomly. And it is possible that next time the algorithm will have the state here, initial state here. And if the algorithm, so now you are going to restart the algorithm with a random initial state. And then the algorithm will execute again. And if you have 2 points here, then this algorithm will stuck again here. And if it will stuck again, it can restart again with the random initial state. So it will restart again, maybe, because it is random. And if you will get your point here, or you don't have the two states here, only one state here, but again getting initial state here randomly. So either from here you can go up to this peak, or from here you can go up to this peak by that restarting. So now in this shotgun hill climbing, a random restart, whenever your algorithm will stuck on the local maximum, it will restart and it will try to get initial state again randomly. And it is possible that you will have your point here. And if you will have your point here with no any further confusions here on the flat area, and if you don't have the flat area here, then you will reach definitely on this global maximum. So in this version, after restarting, if you will again reach on the local maximum or the solution. I can use the word solution. If your algorithm will restart, you will again reach at the solution. Then you will check that this new solution is better than the previous, where your previous call to this algorithm was halted due to stuck on the peak. Okay, so then you will check this new solution is better than that previous one. If better, you will keep this as a current node and you will discard all the previous. And then in this way you will move on until you reach at the global maximum. So this is how this random restart hill climbing or shotgun hill climbing executes. It will search iteratively, and each time with a random initial condition, it will keep the best solution. Best means it is best than the existing one. And this random state, if you with this approach, you will not stuck on the local maxima. Here maxima is a plural, maximum is singular. Okay, so local maxima means all the local maximum. You will not stuck on that. Okay, you will not stuck on that. If you have many local maxima and you have one global maximum, then this random restart, okay, it will iterate maybe 4 times, 5 times, 6 times,
but finally it will reach at the global maximum. What are the applications of it? You can use it in machine learning for optimization, robots and path learning. In natural language processing, people are using it. So these are the different fields in which you can use this hill climbing. You can use it in computer vision, gaming, business operations, etc., etc. And inshallah, in the next, we will start with this simulated annealing.